Okay, let's dive into this. Have you ever really thought about how a battery works? I mean, how do we take a simple chemical reaction, something that just happens all on its own, and somehow turn that into electrical power? Well, that's what we're going to do today. We're going to build one, right from the ground up.
It all starts with a reaction that honestly looks like a magic trick. So on the left, you've got a shiny copper wire and this perfectly clear solution of silver nitrate. But then you dip the wire in and, wow, look at the right. The solution turns this incredible shade of blue, and the wire gets covered in this fuzzy gray solid. You know what that is? That's pure silver metal, just appearing out of nowhere.
So this happens all by itself, it's spontaneous, there's chemical energy being released right there in that beaker. The thing is, all the magic, all the action is happening right on the surface of that wire. So the big question is, how do we capture that energy? How do we turn this cool chemistry demonstration into a battery you can actually use? To do that, to actually harness the power, we need to zoom in and understand what's really happening at the atomic level. And it's all about one thing, the movement of electrons.
This, right here, is the secret. The reaction is really two things happening at the exact same time. First, you've got oxidation. The solid copper atoms are actually losing electrons and dissolving into the water. Those are the copper ions that turn the solution blue. At the same time, you've got reduction. The silver ions that were floating in the solution are grabbing those electrons and turning back into solid silver metal on the wire. So you see, it's a direct transfer. The electrons are literally just jumping from a copper atom to a silver ion.
Now, that direct jump is cool, but it's not useful electricity. To get electricity, you need electrons to flow through a circuit, a wire. So here's the game-changing idea. What if we could physically separate those two reactions? What if we could force the electrons to take the long way around?
And that's exactly what a galvanic cell is. It's this brilliant device that's designed to do just that. It separates the two halves of the reaction so the electrons can't just jump across directly. They have to travel through an external circuit, through a wire. And that flow of electrons through a wire, well, my friends, that is electricity.
So let's do it. Let's actually build one. We'll use our copper and silver reaction and put together a galvanic cell, piece by piece.
So first, instead of one beaker, we need two. We call these half cells. In one, we'll put a strip of copper metal into a solution with copper ions. In the other, a strip of silver in a solution with silver ions. These metal strips are our electrodes. Then we just connect the two electrodes with a wire. That's our external circuit, the path for the electrons.
Now, these electrodes get special names. The electrode where oxidation is happening, where electrons are being lost, is called the anode. For us, that's the copper. The electrode where reduction happens, where electrons are gained, is the cathode. That's the silver. A really easy way to remember this is an-ox, anode and oxidation, and red-cat, reduction and cathode. It works every time.
But hang on a second. We've got a major problem here. Think about it. If all these negative electrons are flowing away from the copper anode, that beaker's going to build up a positive charge, right? And as all those electrons arrive at the silver cathode, that beaker's going to build up a negative charge. That charge imbalance is going to get so strong, so fast, that it'll just stop the electrons from flowing at all. Our battery would die in a split second. So what's the fix? Well, it's this little guy, the unsung hero of the galvanic cell, the salt bridge. It's really just a tube full of a salt solution, and it connects the two beakers. Its whole job is to prevent that charge buildup. As the anode side gets too positive, negative ions flow out of the bridge to balance it. And as the cathode side gets too negative, positive ions flow out of the bridge to balance that. It's the piece that completes the circuit and keeps those electrons flowing. Okay, so now we get how the cell works physically. But you know scientists, they love a good shorthand. So let's learn the simple, standardized way that chemists draw a map of the entire cell.
It's called cell notation, and it's way easier than it looks. It's just a map of the electron's journey from left to right. You always start with the anode on the far left. That single vertical line just means you're crossing from a solid into a liquid, from the electrode to the solution. The double vertical line in the middle, that's our salt bridge. Then you list everything on the cathode side, and end with the cathode electrode on the far right. Anode, salt bridge, cathode. That's the whole path.
So for the cell we just built, it looks exactly like this. On the left, solid copper anode, a line, then the copper ions in the solution. In the middle, our salt bridge, and on the right, the silver ions in their solution, a line, and finally, the solid silver cathode. Isn't that cool? This single line of text tells a chemist everything they need to know to build our entire battery.
All right, time to put our new skill to the test.
Let's see if we can use this notation to figure out a totally different kind of galvanic cell.
So here's a new spontaneous reaction. We've got solid magnesium metal reacting with iron 3 ions. And what does it make? Magnesium ions and iron 2 ions. Now, notice something interesting here. Nothing turns into a solid metal on the right side of this equation. Keep that in mind.
And here's its cell notation. Okay, let's break it down. The anode on the left looks pretty normal, solid magnesium electrode in a magnesium solution, salt bridge in the middle. But look at the cathode side. We've got two different iron ions in the solution, separated by a comma because they're in the same liquid phase. And then at the very end, PTS. That's platinum.
Hold on a second. Platinum? Where did that come from? It wasn't anywhere in the chemical reaction we just saw. So why on earth do we need a platinum electrode to make this battery work?
Well, this brings up a really important idea, the difference between an active electrode and an inert one. Our magnesium electrode was active. It was actually part of the reaction. But in our new cathode, both the reactant, the Fe3+, and the product, the Fe2+, are just ions dissolved in the solution. There's no solid metal for the electrons to flow to. So we need to add one. We use an inert electrode, like platinum, that's conductive but won't react. It just provides a physical surface for the reaction to happen on.
And this quote really sums it up perfectly. The main point is that an electrode just has to be a solid thing that can conduct electricity. If none of the chemicals in your half reaction are solid, no problem. You just bring in a non-reactive metal, like platinum, to step in and do the job.
So we've gone all the way from a simple reaction in a beaker to the chemist's shorthand for a working battery. Pretty cool, right? So how about one final challenge for you? Here's another spontaneous reaction. Based on everything we've just covered, how'd you write the cell notation for this one? Think about what's being oxidized, what's being reduced, and most importantly, will you need an active or an inert electrode?